Thank you very much. I'm going to talk about a special kind of emergence in this talk, and I want to defend this thesis that is encapsulated in the title of my talk. As Sam mentioned, irrationality suggests indecomposability, and indecomposability implies emergence. So the special kind of emergence I want to talk about is called transformational emergence. It's an account that is most famously promoted by Humphreys in a series of papers and book chapters. And basically, the idea is that a fundamental member of domain one goes through a transformational change that is ontological, changes its nature, and as a result becomes a fundamental member of another domain, D2. And as it will become clear, there should be no general third domain that can explain the behavior of this entity in the first domain, its behavior in the second domain, and the transformation between the two domains. And this is a kind of emergence that doesn't need levels. So I remember Olympia complaining about emergent accounts all involving levels. So I hope that she can relate to this kind of emergence, that because the two domains can exist on the same level, and there could be possibly no hierarchies between them. So let me, to further explain this account of emergence, let me use a knowingly problematic example, that is the example of mob psychology. So the example goes, you have an individual who's a very nice person in the normal society. You never expect that individual to commit like cruelties or gruesome acts, but then you put the same individual in the context of a mob, and then that individual can do anything. So it's possible that individual would commit really bad, cruel crimes. So this has been, at least discussed as one way that this fundamental member of the normal society goes through a change of nature, a transformational emergence, and becomes another type of personality that is a member of a mob with totally different behaviors. So what is the problem here? Exactly the third domain, what I call the third domain criterion. Basically, the criterion is lack of a third domain. And here we might say that we have this third domain of general human psychology that can explain the behavior of that person in the normal society, the behavior of that person in the context of a mob, and the transformation between the two. Of course, right now we do not have this third domain, but basically the idea is that it is possible to imagine that such a third domain can exist, and we might someday strike on that third domain. So we cannot really describe this as a transformation in the nature of the thing we are observing. So going back to the schematic, we have a fundamental member of domain D1 that goes through an ontological transformational emergence and becomes a fundamental member of domain D2. The two domains can exist on the same level, although they can also be on different levels. And the idea behind this is that there is no general third domain, D3, that can explain this transformation. And that is what makes it really ontological. So what are the advantages of this transformational emergence? Why we should care about it? It's an ontological account of emergence, but Humphreys claims that it does not need substantial deviation from the normal scientific metaphysics. So, as opposed to what a mental dualist, for example, would need in his or her account of ontological emergence, this kind of emergence is metaphysically friendly to our normal scientific worldviews. And what good uses we can put this kind of emergence into? So, of course, a good ontological account of emergence is very handy when it comes to anti-reductionism. The emergent entities are ontologically different from base entities, and so the properties and the laws governing the new entity are supposedly irreducible to the base entity, because we are facing a completely new entity. The problem with this account, though, is very hard to come up with well-substantiated examples. And the reason is it's very hard to satisfy the third domain criterion. It's better to say the lack of third domain criterion. It's too long, so I just call it third domain criterion. And the reason it's hard to satisfy that criterion is this counter argument from ignorance. So you might say that in the current state of science, we do not have this third domain, but who knows, there might be a third domain that we are not aware of, and someday we'll strike over on that third domain and we'll explain this transformation. Humphrey's own examples, the good ones that are within the domain of science, he has some theoretical examples as well that I'm not going to discuss because these are theoretical and outside of the domain of science. But two of his better examples, one is electrons in a covalent bond. So he thinks that electrons in isolation are of different nature compared to when they form a covalent bond. They become a fused new entity when they form this new covalent bond. And he thinks that is ontological transformational emergence. I personally think that the third domain criterion is hard to satisfy here because quantum mechanics supposedly can explain the behavior of single electrons and when they form the covalent bond. However, another example that he brings is transformation of a muon to an electron. And there again, one might say that there might be some theories in the background we don't know. But even if we accept these examples, as you can see, these good examples are all within the domain of, like, very close to the domain of fundamental physics. And the question is, can we really satisfy this third domain criterion and come up with good examples that are outside of that domain? Because if they're examples of these kind of emergence are always restricted to the very fundamental, it's very hard to expand its application across sciences and put it to good use in special sciences that are exactly the place we need emergence for. So I pursue two questions in this talk. The first question, can we find examples outside of fundamental physics? And my answer is yes, we can find those, at least in my talk in biology. There might be other places as well. And in general, can we find a marker to identify potential cases of transformational emergence anywhere? And my answer to that question is also affirmative. So yes, we can. And what I'm going to suggest is recourse to rational methods. I have to note here that irrational methods here do not have anything with philosophical rationality. It's a term that I borrow from biological engineering, and I'm going to explain in detail what that means. And I have to also say this disclaimer that this marker is not an absolute marker. It's a probabilistic marker. It raises the probability that we are facing a case of ontological transformational emergence, but I will clarify that further. So let me start with where I think this kind of transformational emergence happens in biology. And that is I think that the very base of it is the context dependence of biological functional modules. So functional modules in biology are units of action. They can be a protein, a gene, even a mutation that does a specific function in the system of in the biological system. And what we know for fact about these modules is that they change their behavior, and that change in behavior can be really drastic depending on the context we put that module in. So one example I've cited here, this is a plasmid. This is an experiment that has been done on the paper I've cited below. It's a plasmid. It's very simple. We have a promoter, we have a fluorescent protein, and the promoter promotes the expression of that fluorescent protein, and you can follow the expression of that protein in the cell that you put this plasmid into. So the researchers put this same plasmid into a few different strains of E. coli, the same species, only different strains. And what they observed is that you get significantly different expression levels of this fluorescent protein. So such a simple unit of function, such a simple module shows drastic differences when put in slightly different context. So to clarify it further, so you can take a battery from your drumming monkey and put it in your alarm clock and be sure that tomorrow morning the clock will ring. You expect how the battery would behave more or less when transferred from one system to another. However, when it comes to biological functional modules, it's not the case. You slightly change the context and the behavior of the module can drastically change. So in terms of our framework for transformational emergence here, the domains are the different biological context, and the entity that changes its nature is the biological functional module. And of course, the change that we see in the biological functional module should be drastic enough and important enough to warrant calling it a change in the nature of that functional module. So here I give you one example, and that example is the concept of epistasis. So epistasis is this concept that the effect of a mutation depends on the very details of the sequence into which it is introduced. So here I schematically show two protein sequences, and these protein sequences, each of these colorful boxes represent one amino acid. Here you can see that these two protein sequences differ only on only two amino acids on the other side of the protein, and we want to make a mutation on the other side of the protein, of another side of the protein here. So we make the same mutation into almost identical proteins, and the phenomenon of epistasis, which is commonly observed in proteins, tells us that we can expect that, of course, it doesn't happen all the time, but you can expect that the effect of that mutation on the structure and the function of the protein can go even in opposite directions. So, for example, you might make a mutation into slightly different protein sequences, and one mutation may help a certain function or structural feature, and the same mutation in the other context may decrease that structural that function, or devastate that structural feature. So it might have opposing, completely black and white functional consequences in two different contexts. So here again we are facing the same problem. Of course, in many of these cases, when you dig the literature, you see that when a biological functional module changes its behavior, we really do not have a third general domain to explain the behavior of this functional module in the first domain, the second domain, and the transformation between the two. We really have to go to that very context to be able to explain why this mutation or this functional module does what it does. But of course, there is this counter-argument from ignorance lurking in the background. So there might be such a general third domain that explains this. We just don't know that. And in the rest of my talk, I want to spend time arguing against this counter-argument from ignorance. And I have to tell that I don't aim to refute it completely. I just want to decrease its warrant and probability. So my strategy is that has two steps. My first step is to say that the heavy reliance on irrational methods in biological engineering indicates that these biological systems that engineers are dealing with are indecomposable. And from that, I want to argue that indecomposability of biological systems implies that those systems can be described only within their own domains, and we cannot have a general third domain that can explain the behavior of modules in general. So let me focus on biological engineering. Here, my focus on biological engineering is really a focus on synthetic biology. That is the most recent wave of biological engineering. So I use biological engineering and synthetic biology interchangeably in this talk. So what is biological engineering or synthetic biology? We can describe it as a recomposition. We know that a very prevalent method of discovery in biological sciences is discovery by decomposition. For example, Bechter and Rickardson have argued for that, and other people. So how that happens? We have this system that does a certain function. For example, we have this gentleman that dig holes, and we want to understand how he does it. So we decompose it into its parts, and then we understand what each of these parts really do in isolation. And we also draw an interaction map, an assembly map, that how these different parts come together and result in the final function. This is decomposition or reverse engineering. Once we understood this, we go to forward engineering. We use the same parts, and we use what we have learned about the interactions and about the circuits that result in the function to put together another system that is very similar to the original system. And this is forward engineering or development by recomposition. And this is where biological engineering comes into picture. So this is, again, the same concept. I just rewrite it in this way because I want to further develop this picture in the next slides. So we have the natural biological system. We understand it by reverse engineering and decomposition. How we understand it, we learn parts functions on their own, and we also learn how they interact together with each other to give us the final function. And then we design a system based on what we have learned and forward engineer an artificial biological system. The problem, however, is that in biological engineering, it always fails. So if you consult any review article on biological engineering, you understand that it's a very well-known problem that that artificially engineered biological system never behave as we expect from the design. So for some reason, the systems that are engineered deviate from the expected behavior. So let me give you one example. I just want to use this as a working example. So this is cooling switch. It's one of the earliest examples of synthetic biology. So in this system, we have this genetic circuit. Two inducers are introduced into the system. Inducer 1 increases the reported protein, and inducer 2 decreases the reported protein. Inducers are some environmental factors that be introduced to the system. And so I don't want to really focus on how it works, but just very briefly, inducer 1 induces repressor 1, and repressor 1, of course, represses promoter 1. Less promoter 1 means less repressor 2, and less repressor 2 means more promoter 2. And of course, more promoter 2 means more reported protein. And in the same way, and this is how inducer 1 results into the increased reported protein. And of course, in somehow similar way, inducer 2 results in less reported protein. The problem with this example was that when Coulin's group tried to develop this, the inducer 1 worked, inducer 2 didn't work. So no matter, they introduced this inducer 2, but the reported protein didn't decrease, and they really didn't know what to do with it. And this is an example that we commonly observe across biological engineering system. So here's how I think we can look at this and use this. So if the underlying reason for the failure of biological system is wrong decomposition, which means if we have failed to identify a crucial part, or we have failed to put these things in the correct assembly, then we have to go and solve this problem by recourse to what I call a productive cycle model. I'm going to explain it in a bit. But alternatively, if the underlying problem is in decomposability, then the solution that we would expect to see in biological engineering is recourse to rational methods. Again, I'm going to talk about what irrational methods are. So basically, based on this picture, we can backtrack, we can look at the practice of science, see what scientists do, and then infer what the underlying reason is for failures of biological engineering. And this is what I'm going to do. So of course, if the decomposition is wrong, we expect that the recomposition would also fail. So we might have missed a crucial part in our assembly, or we might have misassembled parts, and this might be the reason that the system misbehaves. So if this is the case, we basically we expect what I call a productive cycle model. So we go and develop an artificial biological system. It fails to behave as expected. We go back, we start again, we decompose again, and we realize, aha, actually we have missed a part, so let's add that part. And of course, not one cycle of the productive cycle model will give us the result. We have to go through it many times. But after that, we understand how the system works, because each time that we go through this cycle, we learn something new about the parts that are important, and we learn something new about how the system should be assembled. And every time that we recompose and come up with a new artificial biological system, we know why we recompose the system in the particular way that we have recomposed it. We know, we have some a priori expectation of how the system should behave. For example, in the cooling switch, this is completely hypothetical, not what has happened in reality. The Coulin's group might have identified that, actually we need another inducer 2' to be in this interaction here, or they could have realized that, oh no, this thing should be rearranged in some way or another, and this might have solved the problem. But this is not how biological engineering works in practice. When they fail, they do not go back to decomposition. They do not try to basically go through this productive cycle model time and again. They just go to trial and error. They tweak the system. They try to they took the system and they try to come up with better ways to basically they go through this this iterational trial and error and try to find a way, find a system that works somehow serendipitously. So it's like this: you put different assemblies, different parts together, and suddenly you find a part that works. And this has been the case for cooling switch. So they actually tweak this this system again and again. After 3 years, I believe this has been the time they worked on this. 3 years of tweaking, they didn't add any new parts. They didn't change the assembly of the parts. They just realized that somehow these promoters, one of them was overpowering the other, and this was the reason that the system didn't work, but they couldn't explain why this happened. So they suddenly came up with a way that works. So this is what I call a shift from what I call rational methods to rational methods. So rational methods are based on a priori mechanistic understanding of the system, and irrational methods are based on a posteriori observations, and the system works as a black box. So you don't understand the mechanism, you just try until you hit on something. And I explained the experimental part, but there is also, I think, that the shift towards deep learning methods in biological engineering, also another way that we go irrational, but I'm not going to touch on this due to time constraints. So why rational methods fail? The reason is rational methods need decomposability of the system. We need parts that are predefined, that have predefined isolable functions, but we actually have parts that depend on basically function in system dependent way. So and we know that the reason for that is this very dense interaction system that are in biological systems that comes and somehow confounds parse function and makes the parse function completely system dependent. And this is exactly what I mean by a system being indecomposable, that the parts function is so intertwined within the system and so heavily under the influence of the system that basically you cannot understand it if you take it out and treat it as a general entity. You really should understand the part only within the context of that very system. So this explains why synthetic biology fails. So if wrong decomposition was the reason behind the failure of rational design in biological engineering, we would expect productive cycle model to be the solution, but this is not the case. Parts functions are context dependent, interactions are circular and unpredictable, and this is why that we have to go rational and rely on trial and error. So this takes me back to the picture. So we see that irrational development is the solution that scientists pick. Therefore, we can infer, backtrack, and say that the underlying reason is probably in decomposability. And so in decomposability, there are two ways that indecomposability results in transformational emergence. One is, of course, what I have explained throughout the talk, that parts functions are intertwined with the systemic context, and then therefore when we relocate those parts from one domain to another domain, we see dramatic changes in their nature. So they can function in a completely different way. So this is a transformational emergence of the parts. But I think there is another way that transformational emergence happens in indecomposable systems, and that is where when the hodgepodge of parts come together and form an indecomposable unit that cannot be understood in when we separate the parts from each other. So we should understand the biological system as one unit that has been transformationally emerged out of the hodgepodge of parts that have formed that system. So why we don't have the third domain problem here? The system is indecomposable. Parts functions depend on the system. So we should go to the domain of each system to explain the parts functions. And therefore, we cannot have a description of the parts function in general. And that means we cannot have a general explanatory third domain. So just ignoring all the middle steps, we can go from the system is indecomposable. So we cannot have a general explanatory third domain for this. So in formal terms, we see, of course, scientists always prefer rational methods because those are better. They provide better understanding of the mechanistic like the mechanisms underlying the system. So they always try to stay rational But we see that, I suppose that we see that scientists resort to rational methods, and that is what I call E of IR, that's the evidence of irrationality. We can entertain two hypotheses in light of this evidence. The hypothesis D is tells us that the systems are decomposable, but the discipline is immature. We still need time to really find the decomposition that really works. Or we can entertain the hypothesis I, that is the system is indecomposable. So this is how I think the likelihood ratio would change over time. So as the dawn of a discipline, we expect that, yeah, the discipline is immature, scientists still need time to work on it. But then we gather evidence of irrationality as is represented by this cone on top. And at some point, the likelihood ratio tilts in favor of indecomposability. And I've put 2021 because I believe we are at that point for micro-level biology. Of course, this is what I argue for, but I think it works in general. So what if at some point of time we hit on the grand theory of micro-level biology? Suddenly we realize that, how everything in biology works. Well, of course, this will drop. The likelihood ratio will drop in favor of the decomposability hypothesis. But here in response, I want to borrow a quote from Sandra Mitchell, who says, to assume in an argument what we might know at the end of science is to ignore the facts of the history of science and the state of current science. And so I think that until we reach the end of science, we should take Nancy Cartwright's advice and make sure that our metaphysics walks hand in hand with our methods. So therefore, this is what I want to conclude. As long as scientists are obliged to use irrational methods, we should at least suspect that their systems are indecomposable and therefore transformationally emergent. So these are my conclusions. Heavy reliance on irrational methods in biological engineering suggests indecomposability of many micro-level biological systems, that in turn implies transformational emergence in biological parts, and heavy reliance on rational methods can work as a probabilistic marker to find indecomposable systems within science. Those indecomposable systems will show transformational emergence, as I explained, in two ways, in terms of the system as a whole and in terms of parts. So I want to summarize this in this concluding maxim: irrationality suggests indecomposability, and indecomposability implies emergence. And with that, I have to always say that it takes a village to write a paper. So I have to thank many people who have given me fantastic comments, including but not limited to the figures that you see in this slide. And with that, I want to thank you for your attention and patience.